It's my pleasure to reintroduce Agnès Beaudry, who's going to take us on this thrilling ride here. So I advise you to fasten your seat belts now. Thank you very much.
And put away the tray tables. All right. Okay, so I took some time because I got here a little early to write a bit of a summary of what happened yesterday. Okay, so in the first lecture, we talked about the first 3 lines. Okay, so we said that, okay, for any homology theory or any spectrum E, we have a localization functor, which is an arrow between X and an E local spectrum, and that arrow is an E equivalence. Okay. And then we said, okay, let's look at some examples. So let's look at, so the first one is the P local sphere. So let's take the sphere and let's invert all of the primes that don't divide P by using this trick that you might learn as an exercise when you're doing commutative algebra, that this would do it. And then localization at P is going to be localization with respect to this example of E. And we saw that this was a smashing localization. So we were able to get it by just taking X and tensoring it with the localization of the sphere itself. Okay. The next example is we looked at the sphere modulo P, which was the cofiber of the multiplication by P map. And that localization we called P completion, and we wrote sub P without the brackets. And the reason for that name is that it can be expressed as an inverse limit of X modulo P to the N, and that's algebraically, that's how you complete, how you P complete. Okay, so now of course that limit is happening, it's a homotopy limit. So things can look different. We discussed how like the homotopy groups might not be just the P completions themselves. All right. And the next example we did was we took E and I wrote K1. So K1 here, we also said that we could do K1 or K mod P. So now we take mod P K theory. So we take K theory, we take the cofiber of multiplication by P map, and we saw that localization of the sphere at that theory was you take P complete K theory, we have Adams operations acting on P complete K theory, and we take the fixed points in a homotypical sense. Okay. So, and then we got the K1 local sphere. So now this one, you can see I didn't tell you I didn't say X sub K1, I didn't give you a nice formula like in the second bullet point. It's because this one's not smashing, okay? So it's not true that you can localize a K1 by just smashing with the K1 local sphere, okay? So this is called the K1 local sphere. Okay, and I discussed a little bit how if you take, without really proving it or explaining it, how if you take P complete K theory, you tensor it with itself and then you recomplete, because that process can take you out of the complete world, you're gonna have continuous functions from these Adams operations to KP. And I misspoke when I said the normal basis theorem. What I meant is for fields, this is something you can just, for field extension, classical Galois theory, it's something that you can deduce it. I looked it up, I'm not gonna give you the proof, but it's, you know, it uses Dedekind's lemma, and also that the dimension of the extension is the order of the group, okay? So in any case, but it's not hard. Okay, so now we talked about this, and here's a couple bonuses before I move on to the next topic. One thing I didn't do yesterday is tell you, well, let's say you could ask, well, what about just localization at P complete K theory? What would that look like? Okay, so I'm going to call. So remember, we're about to change the ones to n's. So I'm going to say, okay, P complete K theory, we're going to call it E1, and you'll see that again in the coming lectures. And these Adams operation, we'll call it G1, okay? And one thing that I didn't say is if you take the Bousfield class of P complete K theory, it's actually going to be equal to the Bousfield class of the sum of these two theories. Okay, so this is something that's proven in Ravenel's fundamental paper on this topic. And for P complete K theory, you can localize by just tensoring with the P complete sphere, with the localization of the sphere at P complete K theory. And this one we could have solved also using a sort of P local construction of the J spectrum. Okay, not quite. It would have been a bit more technical, but this is as simple to describe as when we talked about SK1 being this P spectrum, okay? All right, and then if you want to K1 localize, what do? Well, you localize at P-complete K-theory, and then you P-complete. That turns out to be a formula for that, okay? So the difference between these two formulas is this P-completion, and it turns out that this P-completion is the same as K1 localization. So in other words, to localize at E1, at K1, you localize at E1, and then you localize at K1, the result at K1. Okay, and so now the next goal is, I've stated all these things not necessarily in the way that they appear classically in the literature, but I'm going to be generalizing this. So I stated it in a way that would sort of now hopefully look familiar when I get to the general cases, okay? So now you might feel like there's a lot of things on that board that you don't really understand so deeply, but I want you to reset and be like, no, okay, these things I'm gonna accept them, and I'm gonna be okay with them, okay? And these are gonna be my ground base, okay? And it's okay, like you'll have to spend some time learning them properly, but for now, I want these to be your ground base, and then to sort of tell yourself that you're okay with them so that you can sort of go to the next layer of abstraction, which will be also thick, okay? Does that make sense? Yeah. Okay, cool. I mean, this helps me, right? If I just tell myself it's okay that I don't fully understand, but I can absorb these facts, and then I can move on and work with them. Okay, so that's what I'm going to ask you all to do.
Not only is it okay, but it's very kind.
It is very kind to yourselves. Yeah. Okay, so now my next goal, maybe I'll call this part 3. I'm not sure if we'll finish part 3 in the next lecture. Probably not. But I want to sort of make sense of, what if I said spec S, right? So what are the primes? They're the spectrum in the algebro-geometric sense of the ring Z, right? And if I have any ring, I have a spectrum, which is this prime ideals. There's a topology on it. Okay, so now we're doing algebra in spectra. So now this integers is the sphere. So what's the spectrum of the sphere? Okay, so what should that be defined to be? What should it look like? And so I want to give you at least sort of a feeling for what it is by the end of, in the next hour or so, or 2, okay? All right, so now, but first, it's going to take a bit before we get back there. And I want to remind you of a key tool, right, that we used over there. We had this map. And it was an ISO on K-theory. Okay. And this allowed us to form the telescope, which was our T1. And it wasn't trivial. Okay. So now let's make a definition. Okay. So a self map from a spectrum to itself is going to be called nilpotent. If I iterate it, just like we were iterating V1 yesterday, is null. Eventually it becomes null. Okay. So this one was not nilpotent, right? Because if it's an isomerism on K-theory, it's just never gonna, I can iterate it as much as I can, okay? So if we believe that maybe this was a key ingredient, then we might want to find, so we might want to find non-nilpotent maps. And wonder how they can help us understand various localizations. Okay. Okay, so now here's our next classical player that enters the game. So MU is the spectrum whose spaces are mu0, mu1. Okay, so maybe I should double mu0, but let me not bother. And so on. Okay, what is mun? Is the Thom space of the canonical n-plane bundle, or the tautological plane bundle. BUN. Okay, so BUN is a Grassmannian of n-planes in C infinity, so it has a tautological line bundle, and I can form the Thom space of this. So how do I form the Thom space? I just one-point compactify all the fibers, and then I just crush all the points at infinity to 1 point. Okay, so it's a pretty nifty construction, but you can imagine that, you know, if I had Rn over a point and I took the Thom space, all I would be doing would be wrapping everything up at infinity and getting a sphere. Okay, so it's kind of like a parameterized version of forming. If you have a vector bundle, each fiber you can turn into a sphere. Okay, but then you have a bunch of infinities, and we want to be based, so we just take all these infinities and crush them so that you get a base point. Okay, so that's the Thom space. Okay, so, and really I need to double, so really I should do mu0 sigma mu0 and then mu1 sigma mu2, but this is a spectrum, kind of like in the sort of first definition of spectra you ever see as a sequence of spaces with maps from something to its suspension. Okay, and this is complex Bourdism. Okay, and if I do mu star of a point, which this is what we also call pi star of mu, these are cobordism classes of almost complex closed manifolds. Sorry, I meant okay.
Bourdism, you're dealing well with the boundary of the blackboard.
Yeah. Thank you. I was like, what is he talking about? I get it. Just a little slower. Okay. Okay. So now Bourdism is one of the sort of key tools that appears throughout algebraic topology. So I won't really say more than that, but whenever I use facts about it, I'll just tell you what they are. And okay, so now here's the big theorem. This is the Nilpoten's theorem. It was a conjecture of Ravenel, and it was proved by Devenotz, Hopkins, and Smith. This is from Nilpoten's 1. There's 2 Nilpoten's paper, and it says that, so here's one part of it. Let F be a finite spectrum. And F be a self-map. F is nilpotent. Is it nilpotent or nilpotent? English speakers. Nilpotent. Okay. Is nilpotent. If and only if. So mu star of F, which is pi star of mu tensored with F, is nilpotent. Okay. Okay, so this is part of the statement of a statement that mu detects nilpotence. Okay. So I have a self map, and I want to know, is it going to be good for me, or is it going to be a self map that I can iterate and hope to have like always non-trivial iterates? Well, I can check on mu. Okay, and in fact, I phrased it this way so that it's easier to so that the generalization is easier to see, but it's actually if and only if mu star of F is 0. Okay, so that means mu can be used to sort of test if the things we construct are going to be amenable to the techniques that we did before, okay? So yesterday, somebody told me a story about Steve Wilson being super excited back in the day, trying to convince people how BP theory was computable. Okay, hi, Steve. Yeah, that's great. And I'd be excited to hear more about those stories from back in the day from you. But I'm going to sort of contradict the statement and say that, yeah, okay, it's great to be able to do it with MU, but wouldn't it be nice to be able to do it with an even more computable theory? For example, like a theory that has Kunith isomorphisms, or like just something that's smaller, something that's even better than MU. So this is going to be sort of the theories we're going to introduce next. So we're going to introduce, and they're going to be built from MU, so really they're also theories. So Kn, and then there's actually going to be, we write Kn, but really there's a prime that's implicit, okay, for each prime P, and 0 less than infinity, okay? And the theorem of Hopkins and Smith, so this is in nilpotence 2, and it's the consequence of the first nilpotence theorem with a lot of extra work, is that actually these are good enough, okay? And then I'll convince you that these are nice. Okay, let F be a finite spectrum. And F be a self map. Then F is nilpotent. If and only if K, P, and star of F is for all P and all N's. Okay. Okay, so instead you might be, okay, well, I've traded one theory for an infinitely many, but these, yeah. Yeah, but these, so there's a trade-off, but as we'll see, these are particularly nice theories that are convenient to compute with, and then we're going to use them for more stuff too. Okay.
Are there any other questions?
So I'm just wondering, like, why I should expect this first nilpotence theorem to be true. Like, I mean, maybe the second one, like, okay, I've like fractured at a bunch of like times and heights, and maybe I can assemble all the data together. But why should I like think to even like conjecture that this first one should be true?
Oh, that's a good question. Gee. I wish I had an answer for you. And I know, I'm sure there's a really good answer. I'm just not. I'm sure that gee whiz. Okay, yeah, I don't want to answer that right now. I don't know quite what to say. I don't have that uploaded in my brain.
Yeah, totally reasonable.
But,
thank you.
I'm sure that somebody in the audience might have an answer to that.
Repeat the question for our.
Yeah, so I can repeat it. So the question is like, why should I expect to be, what's the intuition behind the first theorem? Why should I expect to be true? It's a great question. And I honestly should have thought this through before, but I'm not going to answer it. Yeah. Okay.
Are there any other questions, please? Are there any questions online from our online audience? Does anybody have a question or want to say something? Who is the question? Excuse me, sir. Could you repeat that?
Yeah, just asking what the intuition for the second theorem is,
So-
because he seemed to understand it very well.
So maybe I'll say, you could think of this as like being like F, let's pretend like this means like F mod the prime. So these are gonna be, so one step ahead, these are gonna be like the primes of spectra. Okay, that's where we're going. Okay, so these are gonna sort of, and this is kind of like, let's imagine this as like, you know, like F model, like F is nilpotent mod the prime or localized at the prime or whatnot. So then you can say like, oh, okay, the intuition would be that it's true at all primes. And therefore by some like global to local principle, that's true in general, right? Yeah, so, okay. But why would MU know about all of this together? I mean, MU really is kind of like governs, I mean, if we can go back, we can do an ahistorical sort of intuition for this is if we're like, okay, this makes sense because something should be checkable. This feels like something that should be checkable at all primes or something. And then you're like, oh, okay, well, MU, as we'll see, contains the information for all of these guys, so kind of governs all of them. But that is not how it went historically. Yeah, it probably has to do with vanishing lines in spectral sequences and stuff like that. But yeah, okay. All right.
Oh, sorry. Thank you.
Are there similar results for non-finite spectra? So this is just this particular statement for nilpotence is definitely needs F to be finite. So there's, in Doug's paper, there's a counterexample for non-finite spectra. It's counterexample built out of MU. So there's other formulation of nilpotence, like what it means to be nilpotent. Like, for example, you have a ring spectrum and you have an element in its homotopy. You might ask, what does it mean for that to be nilpotent? Well, the homotopy is a ring, so it means that the element is nilpotent, and there's a theorem about nilpotence for that, and there's no finiteness condition on the ring. There's also like conditions about if you have a map from a finite spectrum into another spectrum with no condition, and you know that if you smash it with itself, it becomes null. You know, how do you detect that? And you can detect that as well. Okay, so but there definitely has to be. So for the last two statement I gave, like there was like a finiteness condition, and that condition is crucial and it's important because otherwise the theorem's just not true. Okay.
Yeah, sorry. This might be already mentioned, but might not have caught it. Why you mentioned earlier why MU computation is way harder or like harder than the.
I'm not gonna like make like necessarily that claim. MU is much bigger. It has a lot more information. In particular, it contains the information from all of these. MU does not have like generally a Kunath isomorphism necessarily. We're going to see that these are small. I'm just saying these are very nice for computing. So you want to think of these as kind of like analogs of HQ or HFP. Okay, and we'll get there. Any other questions?
Is there a BP version of nilpotence?
Yeah, if you're P local, then you can just do it with BP. Yeah. So for P local spectra, BP is sufficient. Okay. Okay. And for what people, if you, as I walk over there, oh no, the beautiful red chalk. Okay. Yeah. So if for those who don't know what BP is, I won't really talk about BP this. I'll just stick with MU. But if you localize MU at P, you know this construction, then it's going to split as a wedge. It's going to be a sum of things called BP. And there's going to be lots of redundant information, and you can kind of just strip off a little bit of it. Just like for, remember, K mod P was a wedge of these guys, so we just stripped one off, and that was all that mattered. But you have to work P locally for that to be sufficient. Okay, so now I'm ready to, I want to talk about the Morava K theories. In this, it's just going to be a homotopy ring. So sometimes I say E infinity here. I don't need this. Ring spectrum E is complex orientable. If I look at the map from E2 of CP infinity to E2 of CP1, this is surjective. Okay, there's a lot of definitions out there, but I think this isn't the one that Lurie uses in his notes on chromatic homotopy theory, and is very neat. it's very clean. Okay. So why do we think about complex orientable spectra? These are spectra that will have, so all of the complex bundle are going to be orientable. They're going to have Chern, like orientable in that theory. They're going to have Chern classes and stuff like that. Okay, so these are like really, because of that, like whenever you have a theory of Chern classes, you can use these to study vector bundles, and you can hope that the Chern classes for that theory tell you more than the classical Chern classes. Okay. All right, so now using the Atiyah-Hirzebruch spectral sequence, one can deduce that for one of these guys, if I take a product of n copies of CP infinity, I'm going to get the cohomology of a point adjoin n variables. Okay, so this is the Atiyah-Hirzebruch spectral sequence will collapse, and you're going to sort of you're going to solve and the limit, and you're going to solve the extension. Like when you're looking at the answer, you take an inverse limit in a spectral sequence, and so you're going to get, that's where the power series is going to come. Okay, that means that if I look at CP infinity cross CP infinity, well, actually, yeah. Okay, so remember CP infinity cross CP infinity, this is an H space. It has a multiplication. So I can use that map to get a map back to CP infinity. Okay, but now I can apply cohomology. It'll flip the map. Okay. And now up there, I get that this is E star of a point on two variables, and this is E star of a point on one variable. Okay, and so my map has to send my generator X to an element in here, so a power series, right, in two variables. So I'm going to call it FE X1 X2. Okay. And there's a neat notational trick that, well, I learned from Doug's papers. I don't know where he got it, if he didn't make it up. So I can just write X1 plus sub B of X2, and that's going to be my definition for this series. Okay. Okay. So this notation, don't make more of it. It's that. Okay. That's my definition. Yeah. Okay. And the point is that this series enjoys a lot of properties, so that I'm going to gather in this definition. So a formal group law over a ring, and in our example, we're looking at the ring E star of a point is a power series. Let me call it F, and then, which we like to write like this. And this is an okay, such that so if I plug in 0 in one of the variables, I get X, and I get the same thing if I plug in 0 in the other variable. X plus X1, X1 plus X2 is the same as X2 plus X1. So there's a symmetry. And if I iterate plugging in like so, I'm going to have the same thing. That's it. Okay. So what does it look like? Yeah, it's a. It looks like the rules for an abelian group, right? Okay. And in fact, like a formal group law, it's a power series in this guy. And if you take like spoof, which is the same as spec for power series, you switch the arrows and you think of everything, and if you think it through, that data is actually going to give you a group law on the spectrum or the formal spectrum of R adjoint one variable. Okay, so that's why like it's a formal group law. Okay, it's a group law on the formal spectrum. Okay, so the reason this has these property is that, well, the H-space structure on CP infinity classifies the tensor product of line bundles. Okay, tensor product of line bundles is commutative, so that means that if the H-space structure is commutative up to homotopy. Okay, tensor product is associative, so I get associativity. If I tensor with a trivial bundle, I get the bundle back. That's the zero. Okay, so that's one way to think of why this has these properties.
Okay, we have a comment. Online. You may want to assume E is homotopy commutative.
Oh yeah. I want.
Then it's not.
Sorry. I mean, yeah. Of course, I want E to be homotopy. Thank you.
Thank you for that online comment. The students, if you take complex K theory is complex orientable. And so the complex K theory of a product of CP infinities is easy. But the KO theory is not complex orientable. And so the KO theory of a product of CP infinities is extremely complicated. It's sort of basic example.
I'm going to do one more definition, and I'm going to do some examples, which will include complex K theory. Okay. So let me make a definition. If I do P f of x is going to be, I just iterate this P times. Okay. This is called the P series. Oh, I want to say this. Okay. So I just iterate plugging x into their P times. So then I get a power series in one variable, right? Okay, so it's a power series in one variable, and you can check that, well, this condition tells you that this power series has no constant term. And then from this, you're going to get that this is equal to, well, okay, so you're going to get, I'm going to call it V0. The first term, the first non-zero term is going to be non-constant, and I'm called this V0, and you're going to be able to check that that's actually just P, okay? And then plus, there's going to be coefficients. Then there's going to be a coefficient for x to the P, and then there's going to be a coefficient for x to the P squared, plus, in general, I'll write Vn for the coefficients of x to the P to the n. Okay. Okay, the VIs, right? They're coefficients, they're in the ring. So there's some elements in R, and in the graded setting, so maybe the VNs, in the graded setting, they're going to have degree 2 P to the n minus 1. Okay. That's just, I don't want to get into the technical details of the grading, so I'm just going to kind of ignore that a little bit and only just tell you about grading when it's important. Okay, so whatever those are, there's something, okay? And, you know, but you should like be alert to the fact that I just called them VIs, and we had the VIs from before, and they're going to be all related. Okay, so now I want to go through a couple examples of formal group laws and talk about that. So let's. Any R. HR is complex orientable. Okay, so just regular cohomology. And then with, okay, so then its formal group law has a name. It's called the additive formal group law. And it looks like this. Okay, so what do we get? If I do this p times, right, I'm going to get px. Okay, so I just plug x into, I plug y is equal to x once, I get 2x, 3x, 4x, px. So I get that v0 is p. Okay, and all of the other vi's. And it's bigger than a 0. Okay. KR. Okay, so all I mean here is K-theory with coefficients in the ring R. I don't mean real K-theory. I don't mean like don't mean a TR real. I don't mean anything. I just mean like K-theory with coefficients and R. Okay. I don't mean anything fancy here. Certainly not real real K-theory. This is complex orientable. With, okay, its formal group law is called the multiplicative formal group law. Okay, so let me just write K. So so is going to be, okay. So remember, I have my bot class, right? And I've been calling it U. Okay, so the formal group law looks like this. Like this. Okay, so if you think about the real numbers and their multiplication, okay, so that has it, and you write a chart for that the multiplication is continuous, and you write a chart for the multiplication at 1. Okay, well, a chart would be given by you take x, you do -1, okay, and then you do the addition, and then you move yourself back by adding 1. Okay, so this is what this formal group law is. If you write what I just said down carefully, you're going to get, forget the u, you're going to get x, you're going to get that the multiplication has locally looks like x plus 1 times y plus 1 minus 1. Okay, you just write down just like a little a little algebra exercise. And the u is just that we're in the graded context. The u just puts everything in the right grading. Okay. The reason I put it there is that if I didn't, we would get a confusing answer for the next thing I'm going to write down. So you can play around with this, and you're going to get that v0 is equal to p, and you're going to get that v1 is equal to u to the p minus 1 modulo p. Okay, and then vn is going to be 0 for n bigger than 1. Okay. Okay, so but now this equation v1 is equal to u to the p minus 1, we've seen it. We saw it last time. Okay, so let's go over here. So remember, we had k mod p was the sum I is 0 to p minus 2 sigma 2i k1, and we have k1 star was fp v1 plus, where this v1 here was equal to u to the p minus 1 in the coefficients of this thing. Yeah. Yeah.
Just to clarify, K-theory with coefficients in R, you start with complex K-theory, KU, and then you smash with the Moore spectrum that has homology R in degree 0, the one you denoted sphere R
Yeah,
yesterday.
that's it.
It's okay.
That's
It's just
all I
that.
need.
Perfect. Thank
Yeah.
you.
Are there
Okay.
any questions online?
Okay, I want to do one more example. MU is complex orientable. With what we call the universal formal group law. Okay, so what does that mean? So if F is an FGL over R, then there exists a homomorphism from mu star or pi star of mu to R such that if I do the following, so F is equal to, I'm going to explain what this notation means, F star of mu, where this just means apply phi to the coefficients. Okay, and the contravariant looking notation just comes from the fact that although this is covariant on rings, that makes it contravariance on spec, and the variance for the notation is coming from the geometry. Okay. Okay, so that's what it means to be that. Okay, and what this is a theorem of Quillen, celebrated theorem of Quillen, and I'm not going to go into more of it, but mu knows about all of the complex oriented theories, and it carries the universal form of group law. Okay. Now, I want to talk about the VIs. I'm going to fix a P, and I'm going to localize the homotopy groups of mu at P, or mu at P, and I'm going to look at homotopy groups. Well, the homotopy groups of mu, they're polynomial on a countable collection of generators where the TIs have degree 2i. Okay? Yeah, I'm going to say. So if I localize at P, I just localize the coefficients, so I'm going to get the localization. Okay? Okay, so now we can actually choose generators. So it's possible to choose generators in the P local ring such that T of P to the n minus 1 is Vn. Okay, so what I'm saying is that if I look at the P series, I get some things. These are polynomials in the TIs. Okay, for degree reason, they can't have any terms that are higher than P to the n minus 1. And then you argue that the coefficient is a unit so that you can just change your basis for your choice of generators in your polynomial ring. Okay, so you can arrange it so that they're just equal. So what are the VIs? There's just the P to the n minus 1 generator in this ring. Okay, I'm writing just in general, like writing the coefficients of the formal group law or of something like that in terms of these generators, just like in general, can be kind of nasty. Okay, you get these gross formulas. This is, Quillen's theorem is not trivial. And if you try to like just play around and prove for yourself that if you look at the universal example of a thing like this, that the coefficients of it, the coefficients are going to be restricted by these relations, and that what's left is actually a polynomial algebra on countably many generators. So this is Lazard's theorem, not Quillen's theorem. That's kind of like, sorry, I'm talking about Lazard's theorem right now. It's tricky, okay? You can sit down, you can try to do it, and you'll see it'll be tricky, okay? So, right, so now I want to make a definition that's extremely important for this field. Let's see, I think I don't need the top board. Oh, and as Tony said, so if you want an example of something that's not complex orientable, you can take real K theory, KO. That's not complex orientable. Okay, so let's make a definition. We're going to fix a prime P, an FGL over a P local ring. Has height, has, okay, a P height. greater or equal to n if vi is 0 or I is less than n, less than or equal to n if Vn is a unit, and equals n if it's less than or equal to n and greater or equal to n, okay? Okay, so if, yeah. If and vi is 0 for I. Yeah. So both of them, okay? All right, this feels a little weird if you think about it in terms of like ordering and stuff, but these conditions are mirroring not so much an ordering as conditions for open and closed subsets of some stack, okay? So that's why they kind of look a little weird, okay? I don't want to say more about that, but just don't worry, this is a definition, and that's that. That's just how it's going to be defined. So, and if E is complex orientable, we say E has height n. Sorry, greater or equal to n, equals n, or less than or equal to n, if Fe does. Over. Okay, and here I want P local. All right. Questions? Yeah.
So we're very stupid. I was waiting for like to see the examples, but even after seeing examples, it doesn't make sense. When we say that formal law group, right, or formal group law, there are no inverses, right?
These come automatically, it turns out.
I couldn't hear.
There is an inverse, sorry. There are inverses, they're just automatic, so I didn't put them. I could have added a line. I think I didn't erase it. I just don't need to assume it comes out because power series are easy to invert.
Okay, yeah.
Yeah, so there exists I of x in R x, and actually such that I x plus f x is equal to, you just solve.
Yes. Yeah.
And
okay. Now it makes sense.
Yeah.
Thank you.
good question, no?
There are questions online, please? Okay, thanks.
Okay, so I won't go for too long before our break, but I do want to make our definition for this part is that we're going to fix P and n greater or equal to 0. Okay, so first we're going to define K infinity to just be HFP. That's complex orientable. And Kn, K again, because it depends on P, sometimes it's useful to remind ourselves of that. So what are we going to do? We're going to take mu, we're going to localize at P, and now we're going to kill all the TKs such that TK is not equal to P to the n minus 1, okay? So that means that here, only T to the P to the n minus 1, which is Vn, is left, okay? And then we're going to invert that one that's left, okay? And so let's look. So if I do K0, okay, well, what did I do? I killed all of the TIs except for T0, okay? And then I inverted T0, but T0 was V0, which was P. So I just inverted P. Okay, so K0 is just rational cohomology, okay? And this is, for all P, it's the same, okay? Because all the primes end up being inverted. Okay, so now the next example, so let's see if I do K1, K1, okay, so what's left? So I had all of the VIs and I only kept V1, right, which was in degree P minus 1, okay? And then I inverted it, so the homotopy groups of this thing are gonna be V1 plus or minus 1, and this is the same V1 as above, right? So this has a map into K mod P star, and it actually comes from a map of spectra. Okay, so this is mod PK theory. So V1 is a sum n, is, let's say, R sum n from before. Okay. And so great, so we've already seen one of the primes. Okay, and in general, so if I look at Kn star, if you think through, you're going to get Fp, and then you're going to have Vn inverse, sorry, Vn plus or minus 1. Okay, so this is the coefficients are very small here. Okay, it's just a graded ring, and let's put the degree of Vn. It's a graded ring. It's a graded field. Okay, graded field. Okay, let me see where a good. Okay, and then I'll state a theorem. The Kn are complex orientable. Homotopy rings. Of height. N with coefficients equal to, okay, I already wrote that, sorry, of height n. Okay. So let's look at an example. Okay, so let's look at K0, right? K0, I've got, it's gonna have it's HQ, so it's got this formal group law, okay? And let's see, V0 is a unit, okay? And then the VIs are 0 for n bigger than 0, so it satisfies this condition, okay? So K0 is height 0. Let me not write that because it's in the thing. Okay, so what's the other example? So K1 we already did. So so if I do K1 mod PK theory, right? Okay. So sorry, the important part was that the VIs are 0 for I less than n, but there's no condition there. So if we look at this one, right? Well, mod P, right? V0 is 0, and then V1 is a unit. Okay. So it satisfies our condition, so it has height 1. Okay. Now let's look at the next example, which is infinity, because we like everything in between is like a new theory. Okay, it's something that we haven't discussed yet. For infinity, we're back in this case, right? And then V0 is 0, all the VIs are 0. Okay, so now you need to like extend your mind and check that. Okay, so that the reasonable definition for that would be height infinity. Okay, and make that your definition. Okay, so that's the KNs, and then after the break, so at 11:30, we'll start talking about their properties and stuff like that.
Thank you very much.